Yeah, 5 properties of binary trees. That's right. Okay. So now after the test, we're going to continue with binary trees and the 5 properties that they have. Oh, it's not letting me. Apple Pencil. Okay, there we go. Binary tree properties. I suppose as a quick rehash, a binary tree is a tree that has 2 children. It can have less than that, but up to 2 children. We call that, if we have something like this, we call this a parent node, and we call these 2 the child nodes. We also call the ones that don't have any children leaf nodes, and then any ones that do have children, we call, such as this one, or if we had something like this, then this is a leaf node, and then these 2, all these, we call internal nodes. And so those are the 2 sort of identifiers that we use. And then in addition to that, what else did we say? I think that was pretty much all. Well, I showed you some pseudocode of how to actually declare a node, in a binary tree node versus a linked list node, which eventually looks kind of like a double linked list because there's 2 pointers, left and right. And we don't really use the terminology, but you could say that this up here, this is the grandparent of this node. And we can also say this is the grandchild of that node, right? So we don't really use that terminology because it's kind of weird. Maybe with ABL trees we might, but maybe I would say the parent's parent instead, and so on. But yeah, okay. So from there, now we're going to talk about these 5 properties. And these properties are useful because they let us understand a little bit better about how binary trees work and some of the sort of facts that they have. So let me go ahead and write the first one, and then I'll talk about it. Lobe. And you don't want to call it B tree because that's a completely different thing. So beware of that. So the maximum number of nodes at level L of a binary tree is L minus 1. So what is level of the tree, first of all? Well, first of all, if we have a tree like this, everyone remember what this node is specifically called? Root, that's right. So that's the root of the tree, right? And so when we're talking about levels, we are saying that we're kind of splitting the tree sort of by generations. And so the root is going to be the first generation, or 0 generation, depending on how you're counting. And then the next generation is going to be these 2 nodes right here. So that's 1 level. And then the next generation, these 3 nodes, or 4 if there was one here, are going to be the next level. And then these will be the next level, right? Be careful, because if you're drawing really bad, like me, you might get very easily confused, right? So like, for example, there, this is a level. This is a level. And then which of these are levels? Let me number them. 1, 2, 3, 4, and 5. What's the next level? 1, 2, 3. What's up?
So some of them you only have one
child? Yeah.
Is it assumed that the node has 2 pointers and one of them is pointing to null?
Yes, implementation-wise, that's just exactly what you would do. If you're implementing a binary tree node, just like if you're implementing a linked list, the last pointer of the linked list is going to be pointing to null, right? The next pointer. So like if you have a linked list, and this is the last element, that next pointer is set to null, right? That's how you indicate the end of the linked list. And this is, in a way, it's a tree, actually. You can think of that as a tree, and then this is the leaf node. And then this will be your root node, the head pointer. So yes, that's correct. Okay, so yeah, so basically be careful with the levels because you have to kind of keep them, right? You know, if you're drawing it, it's very easy to get confused and say like 1, 2, 4, and 5 are the same level, but they're not. So, okay, so now that we know what levels are, what the property is saying is how many nodes can we have in a binary tree that's a certain level? So let's go ahead and say that we have 3 levels. And let's see what this will tell us. Well, if we have 3 levels, this is saying that 2L minus 1 is going to be the same thing as 2 cubed minus 1, which is equal to 4, right? 2 squared is 4. Okay, so this is saying that the maximum number of nodes that we can have, that does not seem right. Okay. At level L of a binary tree is that 4.
It would be the sum of the previous level.
Ah, sorry. Important letter here, or word, at level. Yes, yeah. So in my head, I was thinking adding all the levels together, but no, at level. So it's saying the maximum number of nodes at this level, not the summation of them, okay? Not adding them, at this level, okay? So yes, that's correct. Level 3, here we have level 1, level 2, level 3, and yes, we have 4. We can't have more, right? Because the number of nodes up here are 2, and there can be more than 2 up here because it's a binary tree, right? So that makes sense. Okay. Notice though, we are considering the root to be level 1, okay? So if we had an empty tree, then we could say that's 0 levels. So this is like the American way of like parking garages, you know, where like bottom floor is level 1 and then second floor is level 2. Whereas in Europe, you know, they have like ground level and then they have first level is actually the second floor. So be careful about that because especially when we talk about height in a second here, you can represent it both ways. Just like you can represent the building in both ways, right? Just you shift everything by 1. So in this case, we are considering that per se the bottom floor is level 1, and then the next floor is level 2. So like American system per se. Okay. So there's a proof by induction on this. So I'm going to go ahead and write it. And I guess we should add a little thing here saying level of root is 1, because we are making that assumption, right? Otherwise we're saying like the European way or something. So how do we prove this? Well, I mean, it seems clear. Oh, what's happening? It's just frozen.
Does that like proofs?
It does not like proofs. I think it's the metal from the bracelet is doing things. Yeah.
Wearing a bracelet.
So watch. So okay. So this can be proved by induction. Okay, so the proof is as follows. Oh, it's doing it again. I don't know. Okay, interesting. I did change the tip because I did run out the tip. So for root L is equal to 1, number of nodes equal to 2L minus 1 is equal to 1. So we're saying in the case of the root where we basically said that the root is level 1, we're saying that the number of nodes that you can have at that level, which is at the root level, is 1 minus 1, which is 2 to the 0, which is basically just 1, which is a statement because we're saying that at root level 1, there can only be 1 node. Okay? So that's the first part of the proof. The second part of the assumption. So the assumption that we're about to make here we might have to not do recording because something is wrong. Here, let me try to see if it's this, the reason why it'll take this off. There's like a delay. Sorry about that. Okay. So we're going to assume that the maximum number of nodes on a level L is 2 to the L minus 1. This is our assumption, okay? And in fact, I'll put it like that so it's easier to read that. That's our assumption in the proof. We're assuming that the number of nodes on level L is 2L minus 1. Now, here's the important part of the proof by induction. Since in a binary tree, every node has at most 2 children, right? Because it's a binary tree. Then the next level would have twice that number of nodes, right? Because it can have at most two children, right? So that's times 2. So we're saying 2 times whatever we had before, which is 2L minus 1. Because this is 2 here is basically another exponent that you're adding to this. It's like this was the same thing as saying 2L minus 1 plus 1, right? You bring it up, which is exactly what we're saying up here. 2L minus 1, which is every time you go a level, you increase it plus 1 there. So there's your proof by induction. Any questions on that? Okay, so let's hope that the pencil doesn't die. I'm going to get another pencil. It's good to have as a backup. Okay, so the next one is going to look very similar now. Except this time, we're talking about height and not level. And now we're saying what I was thinking before, in the sense that we are adding the number of nodes. Okay? So this is saying the maximum number of nodes in the binary tree, so now we're no longer talking about a specific level, but the entire tree of height h is 2h minus 1. Now you're thinking, wait a second, 2h minus 1, the other one was 2l minus 1, but the other one was for levels, right? Well, yes, but now we're going to consider that the height of a tree with a single node is considered as 1. The height of the height of a binary tree with a single node is going to be 1. So I wrote that record. With a single node is 1. So the following tree has a height of 1. This tree has a height of 2. This tree has a height of 3. And so let's try it. Also, big mistake here. That's not in the exponent. There we go. That's what's going to fix that, right? Because otherwise it's going to be like, what? Because think about it. Before, this is giving us the number of nodes in the level, right? But now we're thinking the number of total nodes in the entire tree. And if you think of the relation between this and this, is we're simply getting one more exponent, so 1 more times 2, and then we're subtracting 1. Why is that the case? Because the one that we're subtracting comes from the fact that the root node has only 1 node. It's a special case in the binary tree because every level in the binary tree is a power of 2. We got 2, 4, 8, 16, 32, 64, 128, and so on. But the first level where the root is, that's just 1 single node. And it doesn't matter if this is a binary tree or like a 10,000th tree, ternary tree, whatever. It's always the first case that the root node is just 1 source, single source. So that's why we have that minus 1 there, and that's why we're doing 2 to the h, and we're not subtracting minus 1 there.
So the height of the root would be 0? Because 2 is 0.
No, the height we consider 1. If you want to consider it 0, you can. In that case, So if height of root is 0, you can do 2 to the h plus 1 minus 1. And if you do that, then you can use that formula. But in our case, we are saying that the height of a single node is 1. Yeah, so in fact, it even says here on the notes, in some books, height of a leaf is considered as 0. In this convention, the above formula becomes that. Other thing, when you're measuring the height of something, so like the height of a tree, suppose that I have this tree right here. What's the height of this? What you do is you start from the leaf nodes, or you start, or it depends on, you can do this both two ways, but if you start from the root node, you try to get to a leaf node that's farthest away from the root. So in this case, you're going to go this way, this way, this way, and this way. And then this is farthest away. And now what is the height of this tree? Well, it goes 1, 2, 3, 4. You can say that this is 4. If you're doing it the other way, then, because here's the thing. If you did it this way, and you said 2 to the 4 minus 1, what is 2 to the 4? 16? Minus 1 is 15, right? So we're saying the maximum number of nodes can be 15. Is that the case? Well, let's fill this tree up with everything that it can have. So that would be like that. Then it would be like that. And then that. And then the next level. We need everything at least one more level, right? So we would have 2 more, 2 more, 2 more, 2 more, 2 more, 1 more, 2 and 2. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 times 2, which would be 30, right? Because each of these has 1 node coming out of it, right? So that would be 30 nodes. And so here, we're getting 15. Why? Yes?
5 levels?
Yes, because we consider this to be that extra level, right? So in this case, we're going to say, instead of counting like this 1, 2, 3, 4, we'd count it like 1, 2, 3, 4, 5. And in that case, then this would become 2 to the 5th minus 1, which would be 31. And close enough, 30 to 31. We probably, it's because of this one probably. But yeah. So ultimately, be careful which method you're using, because you might have to use, either this formula or this formula, okay? Now, which one's the one that we're really going to be using a lot? When we get to ABL trees, we're going to be counting from the bottom, actually. So that's the one that we'll actually get practice, which is the one that I am personally used to. Okay, moving on to the next property. So I think it was the watch that was doing weird things, because I took it off and it's fine now. In a binary tree with n nodes, n standing for the number of nodes, you know that from like big O stuff. The minimum possible height or minimum number of levels is log 2 n plus 1. Does everybody know what this means when you're saying something like that? Ceiling function. There's also the opposite, floor function. What it means is take any number that's not a whole number and then round it up in the case of ceiling or round it down in the case of floor. So for example, if I have 2.1 like that, and then the same thing 2.1 like that, and then I have 2.99 like that, and then 2.99 like that. This means round it up. So this actually becomes 3. This rounds it down to 2. This one also becomes 3. This becomes 2. A good way to remember that is when you're working in C++ and you have a float or a double, and you're casting it to an integer, it's kind of applying the floor function because it's just chopping up the decimal, which is what's happening in the floor function. It's just, so I think what's happening is when I go far away from the thing and I come back, that's when it loses like communication. Okay, see like, no, I don't know. Weird things are happening to it. It was fine the other day. So yeah, so basically it just chops off that number, okay? So what this is saying is in a binary tree with n nodes, the minimum possible height or minimum number of levels is the ceiling function of log n plus 1, base 2 of the log. Let's go ahead and test that out. It's dying. Yeah, something's weird is happening. I don't know. It's like I changed the tip, so I don't know if that like did something to it. And the reason I changed the tip was because it was like breaking through. So.
That's what the tip is for.
Well, yeah, but I don't know. See, it just died again. What's that? Yeah, but can't do that right now. We'll just kind of struggle through it today and then figure it out. Or I'll just use the board, but I kind of wanted to have the recording. So, okay. So, let's test this out with the following tree. I really just have a horrible luck with Apple products. I hate Apple products. So, okay. So how many nodes do we have here? We have 1, 2, 3, 4, 5, 6, 7 nodes. So we're saying take the log of 7 plus 1, which is equal to just log of 2, 8, which is equal to 3, right? So we are saying that the maximum, the minimum number of levels, or the minimum possible height of this tree has to be 3. Is that true? Well, we have 1 here, we have 2 here, and we have 3 here, right? Is it possible for us to squish these, keep it as a binary tree, but have less levels? Not really, because everything is full. In fact, everything is full except for the leaf. Let me give you an example of where we'd have the same number of nodes, but we'd have a bigger height. So you have 7 nodes, right? 1, 2, 3, 4, 5, 6, 7. So here we have 7 nodes. We have 1, 2, 3, 4, 5, 6, 7 nodes. But the height is more than 3, right? Or the number of levels is more than 3. In fact, we have 2, 3. We have 4, right? But we want to find out the minimum, right? So the minimum means that we can squish this by taking these two and sort of putting them up here, which is kind of what we had above, to make it become this up here, right? So ultimately, what the property is saying is, if we make this really, really nice tree that's all nice and compressed, how small can we make it? How is this useful? Well, if you're writing an algorithm or you're trying to define, how big, how deep your tree is going to go, then it is useful to know this. Also, the fact that this is log n is going to have a huge play into this, because guess what? If we have a log n height tree, what do you think is going to take if we search the tree, and if it's a binary search tree, to find a number in it? Log n time. So if we're searching for a number in this tree, we can find it in log n time. If we're trying to delete a number, which means searching for it and deleting it, we can do that in log n time. What's the next thing? So we got search, delete, insertion. If there is log n height, it means that at the worst case, if we're trying to insert something into this tree, in the worst case scenario, we're going to have to do 3 comparisons. One there, and then it's either going to be a comparison here or here. And then based on that, we're going to do a comparison here, 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 or here, right? But there's only going to be 3 comparisons ever. One comparison per level, basically. That's log n comparisons, which means insertion, deletion, and retrieval are all going to take log n time, which is much, much faster than anything you can achieve with an array, a vector, or a linked list. So I might have talked a little bit about that before, not sure. But if not, then that's kind of the big play here with log n. But that only works if we have a super nice tree that's really compressed, if we're at that minimum height. If we're not, then this doesn't work. It's not log n, it's going to be n. That's what we're going to achieve when we do AVL trees, is to maintain this to be nice. Okay, so we're at 4 now. Okay. A binary tree with L leaves has at least log L ceiling plus 1 levels. What do you think that means? Remember, leaf nodes are the ones that are at the bottom that have no children coming out of them. They don't technically have to be at the bottom, but you know, you might see something like this actually. In fact, to emphasize it more, let me do one more level. So here we got a bunch of leaf nodes, right? These are all leaf nodes here on this level. But then these are also leaf nodes too. And they're not technically at the bottom per se, but I just want you to be aware of that. So this is saying a binary tree with L leaves has at least log L plus 1 levels. Well, let's see how many leaves we have here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 leaf nodes. And this is saying that we need to have at least this number of levels. Well, what is log 2 of 10? It's 3 point something, right? It's definitely more than 3, and it's definitely less than 4. Therefore, because we have a ceiling function, the ceiling function of this is going to be 4, right? See, that's an important assumption that you have to make sure you can make, because like in a test or something, you see that, you just do it like that, right? You're like, okay, well, you know, we know that 8, log of 8 is 3, and 16 is 4. This is ceiling, so this is something like 3.2 or 3.4. It doesn't matter. Either way, it's going to become 4 because of the ceiling. So, bam. Okay. And then 4 plus 1 is 5. How many levels we have here? We have 1, 2, 3, 4, 5. That's right. So we're actually at the minimum, right? We're at the least amount of levels. Is it possible to make this with 4 levels? Well, we could move 4 of these. We could move those here, but we got 4 more. So it's impossible. So there we go. We could have this to be bigger. Like we could take this branch per se and then just put it like down here, right? We could do something like that. So we could have more levels, but we can't have less. So that's all this is really saying. Okay, 5. In a binary tree where every node has 0 or 2 children, the number of leaf nodes is always, and you'll see this actually will generalize later on to more. But okay, so this is saying in a binary tree where every node has 0 or 2 children, that basically means you see none of these that have 1 children. Okay, so everything is either no children or 2 children. In that case, if we go ahead and we add up all the leaf nodes, there are always going to be one more than the nodes than the parent nodes that have two children. So let's look at this one, because this one has. Is there any node here that only has one child in this tree? I don't think so. So we said that there was 10 leaf nodes, right? 2, 4, 6, 8, 10. How many internal nodes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's one less than the number of leaf nodes. So the property holds true. Now I know I'm a little bit hand waving because of course you're like, well, one example doesn't generalize to every single example, but you can believe that that's always the case. And this can actually generalize to the number of internal nodes as well sometimes. So we'll leave that at that for now. But if you want to prove that, the proof is called, or not prove it, but you want to see the proof. I mean, you can be hardcore and prove it yourself. It's called a handshaking lemma and tree proof. So you can Google that if you want to see proof of that. Okay, so those are 5 properties, and then from there now I'm going to talk to you about a little bit more of jargon, which almost seems like I'm trying to sell something, as you'll see with the names of these, but they're also useful to identify types of binary trees. So the first one that I want to talk about is a full binary tree. These are all common types of binary trees. So what is a full binary tree? A full binary tree is a binary tree is considered full if every node has 0 or 2 children. That's what makes a binary tree full. 0 or 2 children. So is this a full binary tree? Yeah, because we just said that it doesn't have any single parents, basically. So yes, this is a full binary tree because there are no nodes that have one child. They either have 2 children or they're leaf nodes with 0 children. Is that a full binary tree? It is, actually, because the only parent node here, this one, has 2 children. And then these 2 leaf nodes have 0 children. So that's good. That's not a full binary tree because this could have, basically, if you're thinking it from like the implementation perspective, if there's no pointers in anything other than your leaf nodes, then it's not a full. Is that a full binary tree? Just a single node? Yes, because it doesn't have any children, so that's good. I don't want to get into the empty set example of like, is that empty case a full binary tree? No, that's weird. It's like division by 0 or something. So is that a full binary tree? Yeah, it is. I think so because and leaf nodes, no children. Internal nodes here, children and children. So yeah, this is. No, it's not because it's missing this guy. Okay, I think we got the sense of that. So a property of full binary trees is that the number of leaf nodes is the number of internal nodes plus 1, which is exactly the same thing we said actually before here. Just rewording it, but yet, and we basically show you that. Okay. So that's one term that is popular. I guess the upgraded trim level from that is the complete binary tree. So what is a complete binary tree? A complete binary tree, or a binary tree, is considered to be complete if all levels are completely filled except possibly the last level. And that last level, if it's not completely filled, then it has all the nodes to the left side. So yeah, I guess I'll write some of that here. So these are the requirements. All levels are completely filled except possibly the last level, because it doesn't. If every level's filled, like everything, except yeah, like every level is full. You know, the last, like for example, that, then that's considered complete. Okay, but if the last level is not full, it may still be complete as long as all nodes are to the left. Okay? So, this is not only is this a full binary tree, but it's also a complete binary tree. This is also a full and complete binary tree. However, this is where they diverge. Is this a full binary tree? A full? It's not, because it's missing a child, right? It's a single child for that node. But it is considered a complete binary tree because this level is full, this level is full, and then the last level is not necessarily full, but all the nodes are as left as possible. Let me give you an example where they wouldn't be. Now, I've done this by accident before, but how do you actually flip it? Anybody know the gesture for that?
Grab one of them that, like, squares.
I've done it by accident. Who knows?
You go diagonal.
There we go. Oh, no, I didn't do anything. Diagonal. And then flip it. I've done it. It would.
Grab the bottom corner, do you grab the edge, the middle one?
Grab the bottom corner and then
No,
what?
Not the edge, the center.
Yep.
And then, not the center of itself, on the line, there's 3 squares.
Yep.
Yeah, can you grab those?
Yeah, and then go all the way across.
And then try that again from another corner.
Do that from the top.
I don't think we passed geometry class here. I know you can do it. I'll figure that out later. Once I go complain about the pencil not working. There, it's flipped now. Now it's not a complete binary tree or a full binary tree either, because we are missing something here. Okay? So, ultimately, can you fix sort of a tree and make it complete? Yeah, you can. If you want to make it a binary search tree, which, by the way, these definitions like full and complete, they don't necessarily have to be binary search trees. And by that I'm saying it doesn't have to be sorted data. I'm just saying it can be a tree of anything. It could be like the first example that I gave you when we talked about trees was like a computer file system. So you can think back of that example. A file system isn't necessarily sorted. It's just hierarchy that's working on it. So we're saying this is your root folder, this is your CS202 and your CS302, and then from there, this 202 folder only has one thing, and it's there. So how do we fix that? Well, in this case, we really can't unless we go ahead and copy some of these assignments over, here, and then maybe switch that one here too. All I want you to understand is that complete doesn't mean full, all the case, in all cases. Vice versa would also be the case, because that's a full binary tree, but it is not a complete binary tree, right? So they're not necessarily interchangeable. They do cross, if you look at a Venn diagram, there is a certain intersection between them here, but it's not, there's also special cases outside. So we good on that? All right. Two more, or I guess 3 more. So the upgrade from that, I suppose, is the perfect binary tree. So a binary tree is considered to be perfect, in which all internal nodes have 2 children and all leaf nodes are at the same level. That's the one where like everything is just at capacity. So if we took this one, and we just threw in that, this is a perfect binary tree. Because all internal nodes have 2 children, and all leaf nodes are at the same level. I would say that a perfect binary tree can be considered a full binary tree, and it can also be considered a, what's the other one? Complete. So I guess if we update our Venn diagram, nope, that's not a good representation. So let's see. This is a perfect. And then from there, yeah, it became an egg. This is going to be a full, and I think maybe this way. This would be a complete.
Shouldn't all perfects also be complete?
That's what I'm thinking. Yeah.
So you could extend it.
Like that? I think, yeah, there we go. So we got our fulls, we got an intersection there, but we have fulls that are not perfect or complete. We also got complete that are not perfect or full. But we do have full and complete that are not perfect. Actually, do we ever have a full and complete that's not perfect? I think we did. We showed that. Bless you. Well, here, but let's just do a counterexample. Right? That is both full and complete, but not perfect. Yeah. So there we go. Okay. So there you go. Venn diagram, I guess, if that's your thing. I'm not a fan of Venn diagrams. But I'm not a fan of them. It's very easy to forget which circle represents what. And then you're screwed. You're like, it looks like that, but I don't know which is which. So, okay. The important one that we're going to talk about. Oh, actually, before we talk about that one, let's talk about this last one. This is the degenerate or pathological, or what we agreed on Discord and the main tree. That is a tree where every internal node has one child only. That's a degenerate tree. Why? Because remember when I was talking about the log n stuff? You know, if it's a perfect binary tree, then or if it's a perfect binary tree or if it's a complete binary tree, in both cases we have log n height. In the case of full tree, we may not have log n height, but for complete and perfect, we got log n height. In fact, I'll probably write that here. That's probably a good thing to have. So, complete and perfect achieve log n height, plus or minus 1, whatever. A degenerate tree is going to be n height, which is basically a linked list, which means that if we're searching or inserting something, it's going to take n time, and you lose all of the advantages that you gain from your binary tree. So you don't want degenerates you don't want your trees to be degenerate, basically. That sounded weird. So okay, all right. What's that? Oh. All right. So from there, kind of like we don't want the degenerate trees, but what we want is something that's complete or perfect. Or a better sort of definition of that, and that's the one that the ABL trees are going to give us, are a balanced binary tree. That's what we want. That's what we're trying to achieve. What is a balanced binary tree? Well, a binary tree is considered to be balanced if the height, what do you think is that going to be? Of the tree is, tell me, I mean, I've been talking about it. A balanced tree. Log n, yes. Perfectly balanced as all things should be. So, okay. By the way, I think this is obvious, but n stands for the number of nodes in all of these examples, right? So when you see n anywhere, it's the number of nodes. So, let me throw in some examples here. And then I'll actually tell you how to figure out whether something is balanced or not. This looks balanced, right? I mean, you already saw, you can consider any complete and perfect trees to be balanced, okay? So you can consider them to be balanced. But this is neither a perfect binary tree nor a complete one, right? However, this is actually a balanced binary tree. So if you want to go back to your Venn diagram, that's nasty. Let me copy it, otherwise it's going to look weird. And I'm going to use a different color for that. So a balanced tree is going to include all perfect trees all complete trees as well, but not all full trees. But some of them. But those that are included would be considered probably complete. So I think then we will just have an extra here. So the green is balanced. I believe that's about right. Because here's the thing. There are examples here that are considered full, but they're not perfect or complete, that are not balanced, basically. An example of that that's definitely not balanced. When you think of balance, think of like hanging this in a scale from the root. And if it tips to one side, it's probably not balanced. Probably, but there's special cases there.
So there's still binary trees that are balanced, but only full?
There are still binary trees that are balanced, but only full. But only full. Well, if they were, then I would have put it on that part of the Venn diagram, right?
So it doesn't exist at all?
I don't, let's figure it out. Full says there have to be two children, right?
Just 2 or 0.
I think we can give you one example right here. 2 or 0. That is a full tree, bless you, that is not unbalanced. Because let me just double check it. 1, 1, 2, 1. Yeah. Dang. So I guess
That's not balanced? Or that is
that is this considered balanced. So I guess yeah, there's a little bit here. So there you go. Yeah, I'm glad we figured that out actually. Did you know that, or were you just questioning it?
That was the actual question.
That's good. I'm glad you asked that question. See, we learned out of that question. So okay. So let me tell you that figuring out whether something is considered balanced or not is dependent on your algorithm. I mean, yes, the bigger meaning is that it should be log n height. But in reality, what it ends up being is there's two main algorithms that are used for balancing trees. Those are ABL trees and red-black trees. We're going to focus on ABL trees, which is what your assignment is based on. If we have a little bit of time at the end of the semester, we can go back and talk about red-black trees. It's just the big variations are the following. When you're balancing your tree, it's going to involve what's known as rotations, which again we'll talk about in detail, which is basically shifting things around in the tree to make it balanced. So like if it's really heavy on this side, then we're going to take some of these nodes and put them on that side. And also we're just going to decrease the height and make it more log n. So AVL trees take longer time to insert. It's still going to be log n time, but after you insert, they take more time to sort of rebalance itself if it gets unbalanced after the insert. And then they're much faster to access information because they're very tight. Red-black trees, on the other hand, they are faster at inserting. There's less rotations happening. But because of that, sometimes, even though it's quote unquote log n height, it's like log n plus 1 or 2, or it's it gets a little bit off. So when you're actually using these in like applications, if your data is very like insert heavy and less retrieval, you want to go with a red-black tree because you can just keep inserting things. If you are going to insert a few things, but then not really insert a lot, but access more, then you want to use AVLs. So that's just the pro and con, which I'll talk about more when we talk about AVL trees. But I wanted to introduce that. Okay, so what's the way to systematically check, and this is strictly AVLs, whether a tree is balanced or not. So what is this little numbering thing that I kind of just did here? I mean, they look like numbers, but they're like little squiggles, right? What's that? Well, I'll show you. So what you do is, let's just start out with an example here. Yeah, we'll do that. Maybe we'll put one here. Okay. So the way that you check not just the height of a tree, but whether it's balanced or not, is you start from the leaf nodes and you work your way up. And what I'm going to do is, you can, I mean, I don't ever do this step, but I guess I should show it. Is I set all these little values here to 0. These are my heights. I'm considering height 0 here. So remember when I was talking about height, there are two ways of doing it. I'm considering height 0 for the leaf nodes. From there, I'm going to add +1 when I go to the parent. So now, over here, I'm going to walk up. You can see this, right? Okay, I'm going to walk up. In fact, let me zoom in. And I'm going to put a 1 there, because that's a height of 1, because I walked one path up. Okay? I'm going to go to my next leaf node and do the same thing. I'm going to walk up and put a 1 there. Over here, I'm also going to walk up and put a 1 there. And then the next leaf node here, I'm going to walk up and put a 1 there. However, if you're doing this recursively, you probably would end up doing this here. And then you'd want to do this. But before you can do this, you have to do these two. Now that I've achieved these two heights here measurements, I'm going to take the biggest of the two, which in this case, they're both 1. So I'm going to take 1, and I'm going to walk up to the next path and take the biggest number of these two and add 1 to it. So that's 1 plus 1. So it becomes a 2 here. Okay, now I'm going to do this one here. I'm going to take the highest number of that, which is 2. And I'm going to add +1 to it, and I'm going to put it here. Okay? And so I'm going to do this to my tree recursively until I get the height of every single node. When do I know if it's not balanced? Well, let me tell you first when you know that it is balanced. It is balanced when you do this algorithm, and the height difference between the left and the right for every single node is equal or less than or equal to 1. That means if your height difference is 2 or more, it is considered unbalanced. If your height difference is 0 or 1, it is okay. It's balanced. How do you do that in math? Well, just take the absolute value of the subtraction, basically. That way, if you have 1 minus 2 is -1, take the absolute value of that, it's 1. If you had 2 minus 1, it'd just be 1. Absolute value of that is 1, right? So you can use absolute value. If you don't have access to absolute value, you can take the square root, and then you can square it and then take the square root back. But that's like overkill. So anyways, is this balanced? Well, we start out with 0, 0, so that's balanced. When we get here to this node, Is this node balanced? Yes, I just said it's 1, right? So that's okay. We get up here and we get a 3. Is it balanced? Well, we don't know yet because we got to figure out what that is. So let's go ahead and figure that out. To figure that out, we got to figure out what these two are. Over here, this has no children, right? So therefore, we consider this to be height 0 on this side. On this side, however, we don't know because we do have a children, so we got to go there. So we go ahead and we go to the child. So here we have no children and no children, so 0, 0. So then we have 0 here as the biggest number. We walk up here, that's 0 plus 1, becomes a 1 here. Now we can walk up here by taking the biggest number of the two, which is 1, and doing 1 plus 1. This gets a 2. 2 there. Now we have all the nodes have been sort of measured, and it turns out that your root is, 3, 2, which is a difference of 1 again. So therefore, we can say that this tree is balanced. Yay. So we will talk more about balancing when we talk about the ABL algorithm. But next class, we'll talk about traversals first. Any questions? All right. Thank you for watching.